Is there some easy way without representing like this? Because this is that magnetic coupling is there, no?
Yeah.
Doing KVL, KCL is hard with this. I'll always have to go for the Z parameters.
Yeah. Actually, see, we were discussing about T network, etc. So there may be some T network that has same Z parameter maybe.
Oh, I see. Okay, okay, makes sense. Oh, then we can just replace it, no? Whenever you have a transformer, you anyway know that the Z parameters are equivalent.
Correct.
Oh, so you just find out an electrical equivalent.
Yeah.
Here there is some magnetic coupling.
Correct.
You want to find out an electrical equivalent. Okay. Okay, so we want to find out what the electrical equivalent is for the transformer.
Yeah.
Without this magnetic coupling, no?
Yeah.
And you said T network, right?
Just to.
Correct. For an example,
something else also.
But something else also, but let's say T network.
Yeah.
Now only one thing. See, ideal transformer. This is all imaginary.
Yeah.
So the T network should also be purely imaginary components and most likely not a capacitor, no?
Correct.
You have conductive paths for this thing directly,
correct.
the phase shift. So I'm guessing it will look like this, no?
Yeah.
Most likely I'm expecting it to look like this.
Yeah.
Right? Like a T network like this.
Correct.
Only thing is you are saying the parameters of that should be functions of L1, L2 and M. That is right. In terms of the two, for the two port. Perfect. So this two port should be exactly equal to this two port.
Yeah.
That's what you're saying. The only advantage of the right side one, you can apply KVL, KCL, solve equations very easily. Right?
If you want to bring it in a part of other circuit.
Part of a bigger circuit and analyze. Correct. We will give the answer.
I think it's, or this can be a good homework.
This can be a good homework.
To break the head. And then
to break the head. But then how will they know that they have got the right answer? So we'll ask them to do the homework. But what shall we?
We have tried, so we can maybe give the answer.
Correct. So we can do that. Or shall we do one thing? We'll ask it, live session, we'll ask the instructors to give them the answer.
Yeah.
Huh? Shall we do that?
Yeah.
So we want to find out what these values are.
Or the other option is, we can say what are the terms that may come.
Terms.
Let them find out whether those terms are there.
Okay. So we'll give them the answer and let them confirm whether it is there.
Yeah.
Okay, we'll do that. Okay. We'll do that. So
what I meant is, one of these is M.
One of them is M. Correct. So it will be L1, L2 and M will come in all of them.
Yeah.
Correct. I mean, it will come in the components of the network. What shall we do? Okay, let me think of, let's do one of them. So I will think of it this way. So let us say I left the secondary open.
Yeah.
Right? That is like leaving this open.
Yeah.
If I leave the secondary open, there is no I2 of T.
Correct.
That means that the mutual inductance term for V1 should be 0.
Yeah.
Right? Because it is like there is no, well, where is this? di2 by dt is 0 because I2 is 0.
Yeah.
Right? So V1 will only be L1 di1 by dt.
Correct.
So if I look at this T network, I am leaving this open circuit. There is no current through this. So if I actually add these two inductances, it should give me L. Is that correct? L1.
That is true.
It should give me L1.
Yeah.
Whatever these two are, if I add these two, it should give me L1.
That's a very good hint.
Right? It's a good enough hint.
Yeah.
We'll get them. And by the way, this is
same is valid
symmetric.
for the,
Same is valid for the secondary as well.
Yeah.
This will tell them.
Yeah.
And this is common, no?
Yeah.
They should be able to find out.
Yes.
We'll tell them to find out. So, and they should all be functions of the L1, L2, M in the end.
Yes.
Right? Okay. So I think this is good hint. We'll have them do it.
Yeah.
Do the homework to find out what these three components should be.
Yeah.
Okay.